In linear differential equations with constant coefficients, part 1, we have seen how to solve the equations when their right hand side is 0. The roots of auxiliary equations then were real and distinct. In this part 2, we are going to study how to solve LDE with right hand side 0 when the auxiliary equation has repeated roots. Number 2, auxiliary equation has imaginary roots. Number 3, auxiliary equation has real but irrational roots. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. Suppose an auxiliary equation has two repeated roots m and m. So, linear differential equation will become d minus m into d minus m y equals 0. Let us name this equation 1. Now let this d minus m into y is v. So equation 1 becomes d minus m into v equals 0, which is dv minus mv equals 0. But since d means d by dx, it will be d by dx of v minus mv equals 0, which is dv by dx equals mv, which is dv upon v equals m dx. And this is variable separable form of an ordinary differential equation. To solve this, we have to integrate it. So integral dv upon v equals integral m dv plus c, which is log v equals mx plus, for this c we write log c. It will be log v upon c equals mx, which is v upon c equals e raised to mx, or v equals c1 e raised to mx, where c1 is an arbitrary constant. So d minus m into y, which is v, equals c1 e raised to mx, dy minus my equals c1 e raised to mx, that is dy by dx minus my equals c1 e raised to mx. But this is linear differential equation of the type dy by dx plus py equals q, where p and q are functions of x. Here this p is minus m and q is c1 e raised to mx. We have to find integrating factor, which is e raised to integral p dx e raised to integral minus m dx, which is e raised to minus mx. So the integrating factor is e raised to minus mx. Now the solution of this linear differential equation is written as y into integrating factor equals integration of integrating factor into q dx plus arbitrary constant c2, which is y into e raised to minus mx equals integral e raised to minus mx into c1 e raised to mx dx. E raised to minus mx into e raised to mx will be 1. So this will be integral c1 dx plus c2. So y into e raised to minus mx equals c1x plus c2 will be the solution of this linear differential equation. That will be y equals c1x plus c2 into this e raised to mx. So this is the solution of this linear differential equation with two repeated roots m and m. Solve in terms of d. This will be auxiliary equation will be, this will be d plus 2 whole square equals 0. D plus 2 into d plus 2 equals 0 gives two repeated roots of auxiliary equation d equals 2 and 2. Since the root 2 is repeated twice, solution of this LDE will be y equals c1 plus c2x into e raised to 2x, where c1 and c2 are arbitrary constants. Number of arbitrary constants is equal to the number of times the roots are repeated. Solve. In terms of d, this will be taking d square common. D square equals 0, d plus 1 equals 0, gives d equals 0 and 0, root 0 repeating twice, and d equals minus 1. Since root 0 is repeated twice, solution will be y equals c1 plus c2x into e raised to 0x plus c3 e raised to minus x for this root minus 1, which is y equals c1 plus c2x e raised to 0x is 1 plus c3 e raised to minus x. Solve. In terms of d, this will be auxiliary equation will be by trial and error it can be ascertained that d plus 3 is a factor of auxiliary equation. Equating d plus 3 to 0, d will be minus 3. Let us verify minus 3 is a root of auxiliary equation. Substituting minus 3 in place of d, the left hand side of auxiliary equation will be minus 3 raised to 4 minus 18 into minus 3 square plus 81. It is 81 minus 18 into 9 minus 162. 162 minus 162 is 0, which is RHS. Since left hand side equals right hand side, d minus 3 is a root of auxiliary equation, and hence d plus 3 is a factor of auxiliary equation. By synthetic division, let us find the remaining factors. Auxiliary equation in the descending powers of d will be d raised to 4 plus 0d cube minus 18d square plus 0d plus 81 equals 0. Writing coefficients in a row: 1, 0, minus 18, 0, 81. Let us write this minus 3 over here. Write this one here. Minus 3 into 1, minus 3. 0 minus 3 is minus 3. Minus 3 into minus 3, 9. Minus 18 plus 9, minus 9. Minus 3 into minus 9, 27. 0 plus 27, 27. 27 into minus 3, minus 81. 81 minus 81, 0. Since the remainder of synthetic division is 0, the cubic polynomial with these coefficients will be a factor of the auxiliary equation. From these coefficients, the cubic factor will be d cube minus 3d square minus 9d plus 27. So the auxiliary equation is d plus 3 into d cube minus 3d square minus 9d plus 27 equals 0. This cubic polynomial can be further factorized. Auxiliary equation d plus 3 into d plus 3, grouping the terms here, taking d square common, d minus 3, taking minus 9 common, d minus 3 equals 0. D plus 3 into d minus 3 into d square minus 9 equals 0. So d plus 3 factorizing d square minus 9, d minus 3 into d plus 3 equals 0. It will be d plus 3 whole square into d minus 3 whole square equals 0. D plus 3 whole square equals 0 gives two repeated roots minus 3 minus 3, and d minus 3 whole square equals 0 gives two repeated roots 3 and 3. So the solution for these two repeated roots c1 plus c2x into e raised to 3x plus for these two repeated roots c3 plus c4x e raised to minus 3x. So this is the final solution of this linear differential equation with constant coefficients. Solve in terms of d auxiliary equation. This is expansion of d minus 1 cube equals 0. So d equals 1, 1, 1. Here the root 1 is repeated thrice. So the solution of this linear differential equation is y equals c1 plus c2x plus c3x square into e raised to x. Imaginary roots alpha plus I beta and alpha minus I beta always appear in pairs. So for the pair of roots d equals alpha plus I beta and alpha minus I beta, we have the solution of the LDE. Y equals c1 e raised to alpha plus I beta x plus c2 e raised to alpha minus I beta x, which is c1 e raised to alpha x into e raised to I beta x plus c2 into e raised to alpha x into e raised to minus I beta x. Taking e raised to alpha x a common factor, this will be e raised to alpha x into c1 e raised to I beta x plus c2 into e raised to minus I beta x, which is e raised to alpha x into c1. Writing this exponential form in polar form, cos beta x plus I sin beta x plus c2 into cos beta x minus I sin beta x e raised to alpha x into, by rearranging the terms, c1 plus c2 cos beta x plus I times c1 minus c2 sin beta x. So final solution of the differential equation will be y equals e raised to alpha x into, substituting for this c1 plus c2, a, this is a cos beta x, and substituting for this I c1 minus c2 equals b, this is b sin beta x. It should be noted that complex number iota, being a number, has been included in this b. So therefore there is no presence of iota in this final solution, even though the roots are imaginary. What if pair of imaginary roots is repeated twice? Means what if d is alpha plus I beta repeating twice, and alpha minus I beta repeating twice? The solution will be y equals c1 plus c2x, because alpha plus I beta is repeated twice, into e raised to alpha plus I beta x plus c3 plus c4x, because alpha minus I beta is repeated twice, into e raised to alpha minus I beta x. After doing further simplification, it works out to be y equals e raised to alpha x into a1 plus a2x cos beta x plus a3 plus a4x sin beta x. Please note the change which has occurred. a1 plus a2 has been replaced by a1 plus a2x, and a3 plus a4 has been replaced by a3 plus a4x. This is the only change we have to make. When the imaginary roots repeat twice, what if they repeat thrice? It will be y equals e raised to alpha x into a1 plus a2x plus a3x square into cos beta x plus a4 plus a5x plus a6x square into sin beta x. So what we see here, there is a change in the arbitrary constants only, whereas e raised to alpha x, cos beta x and sin beta x remain the same. Solve in terms of d, this will be its auxiliary equation is, which is This is sum of two cubes which can be factorized as d plus 2 into d square minus 2d plus 2 square 4 equals 0. D plus 2 equals 0. D square minus 2d plus 4 equals 0. This is a quadratic equation in D. We will solve it by formula method. For that, A is 1, B is minus 2, constant term C is 4, B square minus 4AC will be minus 2 square 4 minus 4 into 1 into 4, 4 minus 16 minus 12. Square root of b square minus 4ac, square root of minus 12, square root of minus 4 into 3, which is plus minus I 2 root 3. By quadratic formula, d is minus b plus minus b square minus 4ac upon 2a, which is minus of minus 2, 2 plus minus this I 2 root 3 upon 2a, 2 into 1, 2, 2 into 1 plus minus I root 3 upon 2. Cancelling this 2, d will be 1 plus minus I root 3. Here this 1 is alpha and root 3 is beta. From this d plus 2 equals 0, we get d equals minus 2. So there is one real root minus 2 and two imaginary roots. So the solution will be y equals, for this real root minus 2, this will be c1 e raised to minus 2x plus e raised to alpha x, e raised to 1x or e raised to x into c2 cos beta x, that is cos root 3x plus c3 sin beta x, that is sin root 3x. So this is the solution of this linear differential equation. Solve d raised to 4 plus 2d square plus 1 plus y equals 0. Auxiliary equation is d raised to 4 plus 2d square plus 1 equals 0, which is d square plus 1 whole square equals 0. D square plus 1 equals 0. D square plus 1 equals 0. D square equals minus 1. D square equals minus 1. D equals plus minus I. D equals plus minus I. Here imaginary roots are repeated twice. Alpha is 0. Beta is 1. The solution is y equals e raised to 0x c1 plus c2x cos 1x plus c3 plus c4x sin 1x, which is y equals c1 plus c2x cos x plus c3 plus c4x sin x. Solve d raised to 4 minus m raised to 4y equals 0. Auxiliary equation will be d raised to 4 minus m raised to 4 equals 0. Square of d square minus square of m square equals 0. Difference of two squares can be factorized as d square plus m square into d square minus m square equals 0. D square plus m square equals 0, or d square minus m square equals 0. D square minus I square m square equals 0. This is difference of two squares, so can be factorized. D plus im into d minus im equals 0 and d plus m into d minus m equals 0. D equals plus minus im and d equals plus minus m. So the solution y equals, for these two real roots, c1 e raised to mx plus c2 e raised to minus mx. For these two imaginary roots, alpha is 0, beta is m. So its solution will be plus e raised to 0x into c3 cos mx plus c4 sin mx, which will be y equals. Solve auxiliary equation in terms of d square, putting d square equals x, which is a quadratic equation in x. For solving it by quadratic formula, a is 1, b 13, c 36. Discriminant delta p square minus 4ac, 13 square minus 4 into 1 into 36. 169 minus 144, 25. Square root of discriminant delta plus minus 5. So by quadratic formula x equals minus b minus 13 plus minus 5 upon 2a, which is 2, minus 8 upon 2, or minus 18 upon 2. So x is minus 4 or minus 9. So d square is minus 4 or minus 9. D is plus minus I2. D is plus minus I3. For this d, alpha is 0, beta is 2. For this d, alpha is 0, beta is 3. So solution will be y equals e raised to 0x into c1 cos 2x plus c2 sin 2x e raised to 0x, c3 cos 3x plus c4 sin 3x. Finally, solution y will be solve d raised to 4 plus y equals 0. Auxiliary equation d raised to 4 plus 1 equals 0. Square of d square plus square of 1 square equals 0. By completing the square, square of d square, middle term will be 2d square into 1 square plus square of 1 square minus this 2d square 1 square equals 0. This is a perfect square polynomial in D, which can be written as d square plus 1 whole square minus this 2d square can be written as square root 2d square equals 0. This is a difference of two squares which can be factorized as d square plus 1 plus root 2d into d square plus 1 minus root 2d equals 0. This will be d square plus root 2d plus 1 equals 0, or d square minus root 2d plus 1 equals 0. Now these are quadratic equations in D which we will solve by quadratic formula. For that, a is 1, b is root 2, c is 1. So b square minus 4ac will be root 2 square 2 minus 4ac, which is 4. This is minus 2. Square root of b square minus 4ac will be plus minus I root 2. By quadratic formula, d is minus b minus root 2 plus minus square root b square minus 4ac, that is plus minus I root 2 upon 2, which is root 2 into minus 1 plus minus I upon 2, that will be minus 1 plus minus I upon root 2, which is minus 1 upon root 2 I 1 upon root 2. So here alpha is minus 1 upon root 2, beta is 1 upon root 2. This second quadratic equation, only b will change, which is here minus root 2. So d will be 1 upon root 2 plus minus I 1 upon root 2. Here alpha is 1 upon root 2 and beta 1 upon root 2. Now we write the solution. Y equals, for these two roots, e raised to x upon root 2 into c1 cos x upon root 2 plus c2 sin x upon root 2 plus, for these two roots, e raised to minus x upon root 2 into c3 cos x upon root 2 plus c4 sin x upon root 2. Solve e raised to 4 minus 2d cube plus 3d square minus 2d plus y equals 0. Auxiliary equation is, this is an expansion of a trinomial in D. Square root of d raised to 4 d square. Since there are two negative terms here, we will take minus d and square root of 1 plus 1 whole square. Expanding this trinomial, we will check whether we get the same expansion. This will be square of d square d raised to 4 plus square of minus d d square plus square of 1 2 times product of d square and minus d minus 2d cube 2 times product of minus d and 1 minus 2d and 2 times product of 1 and d square 2d square, which is d raised to 4 minus 2d cube, d square plus 2d square plus 3d square minus 2d plus 1, which is the same expansion as this expansion. Hence, we write d square minus d plus 1 whole square equals 0, that is d square minus d plus 1 equals 0, and d square minus d plus 1 equals 0. These are quadratic equation in D. By quadratic formula, D is minus B, which is minus of minus 1 plus minus square root of b square minus 4ac, that is minus 1 whole square 1 minus 4ac means 4 into 1 into 1, that is 4 upon 2a, that is 2, which is 1 plus minus square root of minus 3 upon 2, which is 1 upon 2 plus minus I root 3 upon 2. So here alpha is 1 upon 2, beta is root 3 upon 2. Since there are two such quadratic equations, these roots are repeated twice. So the solution will be y equals e raised to x upon 2 into c1 plus c2x cos of root 3 upon 2 x plus c3 plus c4x sin of root 3 upon 2x. Solve d raised to 6 minus 64y equals 0. Auxiliary equation d raised to 6 minus 2 raised to 6 equals 0. Square of d cube minus square of 2 cube. Difference of two squares is factored as d cube plus 2 cube into d cube minus 2 cube. This is sum of two cubes, which is factored as d plus 2 into d square minus 2d plus 4. Difference of two cubes is factored as d minus 2 into d square plus 2d plus 4 equals 0. This gives d plus 2 equals 0. That gives d equals minus 2. d minus 2 equals 0 gives d equals 2. d square minus 2d plus 4 equals 0 is a quadratic equation in by quadratic formula method. d is minus b, which is minus of minus 2 plus minus square root of b square, that is 4 minus 4ac, 4 into 4 16 upon 2a, that is 2. This is 2 plus minus square root of minus 12 upon 2. This is 2 plus minus 2 square root of minus 3 upon 2, which is 2 into 1 plus minus I root 3 upon 2. Cancelling 2, d will be 1 plus minus I root 3, where alpha is 1, beta is root 3. This factor gives another quadratic equation, d square plus 2d plus 4 equals 0. On the same lines, the root of this quadratic equation d will be minus 1 plus minus I root 3. Now the solution will be y equals, for this d equals minus 2, c1 e raised to minus 2 x. For this d equals 2, c2 e raised to 2x. For d equals 1 plus minus I root 3 e raised to x into c3 cos root 3x plus c4 sin root 3x. And for this d equals minus 1 plus minus I root 3 e raised to minus x into c5 cos root 3x plus c6 sin root 3x. So this is the solution. d square plus 1 whole square into d square plus d plus 1 whole raised to 4 y equals 0. Auxiliary equation, which is, and first equation gives d square plus 1 equals 0, d square plus 1 equals 0, d square equals minus 1, d square equals minus 1, d equals plus minus I, d equals plus minus I, d equals I 2 times minus I 2 times. Accordingly, first part of complementary function y1 is c1 plus c2x cos x plus c3 plus c4x sin x, because for these roots alpha is 0 and beta 1. For this d square plus d plus 1 whole raised to 4 equals 0. Quadratic equation d square plus d plus 1 equals 0. D is minus 1 plus minus square root of b square minus 4ac. 1 square is 1. Minus 4ac is minus 4 upon 2a is 2. Minus 1 plus minus square root of minus 3 is I root 3 upon 2. D is minus half plus minus I root 3 upon 2. Here alpha is minus half and beta root 3 upon 2. These roots are repeating 4 times. So second part of solution is c5 plus c6x plus c7x square plus c8x cube cos root 3 upon 2 plus c9 plus c10x plus c11x square plus c12x cube sin root 3 upon 2. So the final solution y is this whole part. Since the degree of the auxiliary equation is 12, there are 12 arbitrary constants c1 to c12. If you like this video, please like it, share it, and subscribe to this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.